short introduction to the sensor system and also some results from hairpin welding. So I'll start with the technology by itself. It's a photodiode-based sensor system. So we have some light emission from our process that is going back to our laser head, going into our coaxially integrated sensor system. And then we can evaluate the signal on reference base. So we are doing some good welds and say, okay, there's one that shows a little different signal. And then we can say it's not okay because something has happened there. So that's basically how process monitoring with photodiodes work. And our main goals are to increase the accuracy during this monitoring process, because the pseudo faults are in both cases very, very painful, and that is our most important goal to increase this accuracy. The second idea, or the second goal, especially for this sensor, is not just to say, okay, this weld was not okay. We would also like to say, why was it not okay? So we would like to classify the fault, to give some ideas for the production line. Oh, my clamping device is not working correctly. We had a gap between our parts, or our optics has some contamination. And for this purpose, we have designed a new sensor system. You can see it in the picture, and let me. We can see here the welding process with the light emission that is going back into our laser head. And then it is reflected into our sensor system. There we have the first sensor, first photodiode for the laser radiation wavelength. In this case, it's about 1 micrometer. We have another photodiode that is detecting the visible light, and also one for the infrared, near infrared wavelengths. And the last two channels are split into its spectral components. So we have another array of sensors or photodiodes for the near infrared light, and also one for the visible light. So we have 16 channels each. And with this further data, we are able to have a more accurate monitoring compared to our old product, and to hopefully also to the competitors that usually go with 2 or 3 photodiode sensors. So what's the benefit? I already said we have a lot of channels that we can use for the analysis, but we have also developed this sensor in this way that we are able to use it for a wide range of applications that have some process emission. Because the idea is to have one sensor, one hardware sensor for all applications, and to just do some software adoption due to the process or material or wherever you have. So we have tried a lot of different applications, also starting with welding applications for battery cell welding, hairpin welding, which I will show afterwards some results, also bipolar plates or other welding tasks. But we've also used this sensor for laser powder bed fusion, or drilling, or structuring, or coding processes. And we are right now getting some experiences and trying to get some experiences in all kind of markets that are suitable for our sensor system. So our idea is to classify the faults. And for that, I've already shown you that we have a couple of different signals available in our sensor. So what are we going to do with these lot of channels? How we proceed with this one? And therefore, we are going to use a combination of channels. So we have the function in our electronics that we can combine a couple of these channels to create a new channel for the analysis, which is behaving in a special manner for example, for gaps or for spatters or for temperatures. And with this one, we are trying to get some more information, and also for the identification, to get some specific channels for the identification. We are basically getting a lot of data, and then we are correlating it with some scatter bands and say, okay, there's some outlier, and there must something happen during this weld scene. This is of course possible to communicate to the machine, to the logical control, and to say, okay, there was some kind of error. And by having this specific classification of the faults, you're able to also have an adopted maintenance action. So you can say how you proceed with spatters. Maybe you can tolerate them and have just some further check if it's okay, or you can directly send it to scrap when you have a gap between your parts, which will definitely have a huge influence on your quality. So with this, we have a list with a couple of benefits that I probably also told you in the last few minutes. We're trying to reduce the scrap rate, of course. I've talked about the pseudo faults. We're trying to reduce the downtime, of course, because we can faster say what is the root cause of our NOK product. And also we can have a specific maintenance call at the end. So that's it about the basics. Now I would like to talk about some results. In this case, in hairpin welding. So the newest generation of electric engines for electric vehicles are built up using hairpin technology. So instead of winding a wire for the stator, you are stacking these pins, copper pins, into a certain frame, and you welded these frames on one end. So there are a lot of challenges during this welding process. We have investigated more or less all of these ones, but I will just give some shorter results and start with a good hairpin welding right now. On the left side, you can see in this picture, it's going to be a video in a few seconds. This is pin 1, and here on top, it's the second pin. So we are looking with a slight angle on it with a high-speed camera. And on the right side, marked with this arrow, we can see our measurement during that time. I have reduced the channels to have a better visibility. And I will just start the video, and we see 3 weld seams, one on the first pin, one on the second, and then a combined welding. So, and we can see we have some smaller characterization during this weld, but in general, it's a pretty calm process in this case. And now I would like to show the yeah, maybe the opposite of this process. When we have some isolation on this pin that has to be removed before the welding, you can see that the signals are escalating completely, and also you can see the process is not stable at all. And this is something you can see pretty easy. But there are also more complex faults or happenings during the welding that are able to be that are visible in our data. To investigate this, we have performed welding experiments with the Fraunhofer ILT. They are using X-ray imaging to have an insight into these hairpins. We see now one on the left and one on the right. And we are using this data to train our system to get experiences with hairpin welding and how our signals are reacting. To get at the end, of course, more ideas what happens when we don't have this X-ray imaging because it's too expensive for production lines. So I'll start the video. We can see again one weld seam on the left, one on the right, and then a combination of them. And on the right, of course, again, our data is moving. So that was pretty fast, but we'll have a closer look right now. So we can see a couple of peaks during this weld seam. That's good for us because it's not really an okay welding. We have a couple of pores at the end, and we can investigate a couple of things during this welding. Let's start with this very high peak at the end. You can see here the keyhole visible due to the X-ray analysis, because the X-ray analysis shows us the border of our melting pool and also of our keyhole. So this is the keyhole during the welding. And if I move some slides forward, we can see it is moving on the other side, but we've lost the depth completely. And this breakdown of our keyhole we can see here with this very high peak. And one slide afterwards, we are getting back this peak, the depth of the keyhole. So these are things we are investigating with this data. We can also see the positioning was not really good on this side, so the keyhole is bended, and we probably didn't hit the hairpin in the middle, but on this side. Another thing we can do with the sensor is that we have a look on the near-infrared channels. I have excluded 2 of them right now here that we can see in the graph. And what we can see is that they have a different gradient at the end. And with this gradient, it is possible to give some ideas, information about the temperature, because we can build the gradient of it, the quotient, sorry, and then we have kind of a ratio parameter. And this ratio, when it's increasing or decreasing, it gives us some information about the temperature that is, in this case, rising due to the last step of the welding process. And it is basically possible to get also a real absolute temperature, but in this case, this optical setup is not calibrated, so we just can give some relative ideas that we have an increasing edge here. So this is one example for this combination of channels that we are aiming to. And I have also a slide for what we can do with these data with X-ray imaging. Because, oh, that's the video, sorry. Because what we really like to do is we want to skip this X-ray imaging and just have just our data from our sensor and can say on this position and there are happen these kind of mistakes. So what we are doing right now is using artificial intelligence, having these 4 different categories of errors. And in this case, we have trained this model with our data and also the X-ray videos. And this slide here is the result when we just have our data using the trained model. The model is giving us the positions on which we have a higher probability of these 4 categories: porosity, bulging, piercing, and splashing. And we can see that it basically fits very good with this rough surface structure of the weld seam. Also here, it's everything is green, and also the weld seam looks pretty good. And then we have a couple of mistakes in the surface, and we can also see that our signals and the trained model is showing these results. So these are the things we are doing right now. So as in summary, you've seen what we can do. We can provide a multi-spectral process monitoring. We are trying to have one sensor, one hardware sensor, for more or less any application that has some light emission, I would say. And we are trying to use this data for the identification and classification of defects, not just for welding, also for other laser-based processes. So what you can do for us, we are always looking for new applications because we need to prove it that our sensor is possible to deal with a lot of different processes. So therefore, it's interesting for us to get new data from different processes, different applications. We're always looking for scientific or industrial corporations. It would be also interesting for us to get external data to our system because the hardware is generally able to include an external data channel that can be matched and synchronized with our data to have some kind of a data fusion. For example, positioning data of scanner systems. And of course, due to the start of our new product, we are still trying to increase our capabilities in production and calibration and also in optic adjustment. And if there are some experts under the audience, we are open for a discussion. So that's it from my side. Thank you very much. Are there any questions?